Hello and welcome to Easy Projects. So today we'll see if we can turn on a desktop PC using a microcontroller. It could be an Arduino, a Raspberry Pi, BeagleBone Black, whatever you have. But first I would like to say thank you to everybody who supported my channel by purchasing a t-shirt through teespring.com. And if you want one and haven't already ordered it, there's still 2 days left of the campaign from when I upload this video. I will be using the Raspberry Pi because it already has Linux on it, so I can write C programs and execute them like on a regular computer. I can then have this on all the time, and I can access it over the internet, and when I need my big computer I can ask this one to turn it on, and then I can access that over the internet and shut it down when I'm done. There are of course a lot of ways we could do this, and you can get motherboards or plug-in cards that support that the computer can wake up over an Ethernet call or USB or whatever, a mouse press or a keyboard or whatever. There's a lot of options, but the way we will do it is to hack into just simply the power switch with the microcontroller. If we take a look at the connector on the motherboard, you can see we got 2 pins called power switch, but there's no polarity on them. This doesn't matter when you install the motherboard into the computer, because you'll just be using a switch which will short out the 2 pins. So what I have done, and I'm sorry I can't show you this, but the computer is full of cables and the hard drives are in the way, but I just hacked into these 2 cables and soldered 2 extra wires. So I got those here, the green, and so now that I applied power to the power supply, we should be able to just short these together and the computer should turn on. Which it does. And let's just turn it off again. We could simulate a button press with a relay, but most low voltage relays, 5 volt or 3.3 volt, will take somewhere between 100 and 200 milliamps of current. And there's no way these boards can supply that without a transistor in the way. And also we don't necessarily want to burn that much current when it's not needed. So a better choice, since this is very low current, would be to use an optocoupler. I actually don't have one, so we will have to make our own optocoupler or something equivalent. But the way we can test this is with a regular diode. We just connect each end up to each end of the diode, and this will really only work one way around, so you have to remember which way you did it. Yeah, see, it's not like that. So that worked. So the current has to flow from the purple to the green in this case. And that makes sense because I think the green wire was a white wire in the computer. And an optocoupler, we could think of that as simply just an LED and a phototransistor inside a single package. So when the diode is off, no current will be flowing in the transistor. And when the LED is on, if you just turn it on fully, then the transistor will be saturated and your current will get through. We can also make this ourselves just by taking an LED and connecting it to a photodiode and then encapsulating this in a dark environment. We might also be able to do it in another way, where we still use a diode or an LED, and then we hook up a light-dependent resistor instead, and then put this all in a very dark environment. A light-dependent resistor has a very high resistance when it's completely dark. It's in the hundreds of megaohms. And when you shine light at it, it drops to almost 0 ohms. If you have enough light, that is. If I take this LDR and measure the resistance across it, you can see it's 8K in this light situation here. And if I cover it under my black shirt here, you can see it's sometimes it's more than 20 mega ohms, but I'm also touching the leads with my finger, so that's probably why. But you can see it's way up there, so we can consider it an open circuit. Exactly how the circuit inside the computer works, I don't know. But I would guess that we have a high voltage on one of the pins. We can actually measure that. So that would be the purple one. So the green one. And we have 4.7 volts. So what is going on here is that the green wire is a ground wire, and on this purple wire we have a pull-up resistor that keeps this at the 4.7 volts, which is a high. And when you touch these together, you short this to ground, lowering the voltage and activating some circuit in the computer. That means that if we can get this voltage below the threshold voltage, the computer will turn on. As long as there is a high enough resistance between these two, nothing will happen. And also we don't have to get it all the way to 0 ohms, like closing the switch. It's enough if we get the voltage on the purple wire below the threshold voltage, which we don't really know, so we'll just have to get it low enough. So I have a 10K resistor here, and if we try to put this in series with this circuit here, it probably won't turn on, because if they're using a standard value pull-up resistor, this shouldn't be enough. And maybe I should actually turn on the power. That would help. But still, nothing happens. I can try a 1K resistor, and my guess is that it will turn on now. Yep. But I actually don't know how much we need to turn it on, so let's try a 3.3K as well. No? Nothing? 1.5K? Oops. Yep, we got it. So we know that the value has to be below 1.5K for the computer to turn on, and we need to be above 3.3K to be sure that it's not turning on. But we want that a lot higher, obviously. And we can get that. We can get it into the mega ohms range. So I think I'll try it with the LDR. I also have a photodiode, but I think this would be more fun since I've never tried that before. So I'll go and make a little enclosure on the 3D printer that we can put the two parts into, and that will make it sealed inside a dark environment. So I'll be back in a minute. So we're just printing out a housing to hold the light dependent resistor and a white LED. And if you want one of these yourself, you can download the file on my Thingiverse page and print it out yourself. I would of course print it in black to get as little light into there as possible, but I had the white filament in the printer, and it's just a test anyway. And that's also the reason that I don't use my DIY 3D printer, because the filament that I have in there is transparent. So I'll just see if it fits and if the idea works, and then we can print one out in black. And here we have it. But as I said during the print, it should probably be black to block as much light as possible. But let's see, this should go in here. And I just drilled the holes out, so it's a nice fit now. So we can see that's sitting nicely in there. Then we need to find a diode. I'll just use a white diode. So now this sits very close to the photoresistor, and there should be a very high difference between it being on and being off. And yes, I will go and change the battery in the multimeter. But you can see when it is enclosed in this white plastic, we get around 30 kilo ohms of resistance. And if I just hold my hand over it, it jumps up a lot. But of course the end is open and the diode is clear, so if I hold this up to the light, sure enough it drops. So we want to close off the end here. And you can see just by doing this it goes all the way to 80 kilo ohms, which should be fine, but I really want it higher than that. We know we can get this better, but we need to see how much resistance we have when we turn on the LED. So I'm giving this around 15 milliamps, which shouldn't be that difficult to get with a microcontroller. So we get around 600 ohms. I have hoped that it would be better than that, but then again it should be good enough, since we're down to half the resistance we need to turn it on. So it has a voltage drop of 3 volts at 15 milliamps, and we can get that with the Raspberry Pi. It works on 3.3 volts, and it should give us 3 volts at 15 milliamps. I will of course check that this is allowed to supply 15 milliamps. So I just checked, and up to 16 milliamps should be fine for each I/O pin, but only 50 milliamps in total. So if you want to use small pins, then you have to lower the current, because else we could only use 3 pins. If I need to, later I can always add a transistor, then there's no problem anymore. But I want to keep the circuit as simple as possible for now. So we have our 3.3 volt on the Raspberry Pi minus the 3 volt drop on the LED. That gives us 0.3 volts. And if we divide that by the current, which is 15 milliamps, we get a resistor of 20 ohms. So I'll take a 22 ohm, so we're on the safe side and below our 16 milliamps. And of course if you do this with the Arduino, which is operating at 5 volts, then you need a larger value resistor, of course. Just do the same, 5 minus 3, that's 2 volts, 15 milliamps will give you some resistance value. And you might be thinking, why not just hook the ground up to the ground of the Raspberry Pi and then connect the purple wire to one of the I/O pins, and we can just pull it low and the computer will turn on. Well, we could do that and it would work, but then the two are not isolated from one another. And it could mean if something goes wrong with one circuit, it could very likely take out the other circuit. And it's just bad practice to do that, so that's why we go to the trouble to use an optical isolation. And also to prevent noise from getting from one system to the other. In this case I don't think we really care about that, it's more about the protection. And you can see even with the heatsink in there, we only got around 40 k ohm of resistance. But I'm pretty sure just adding some black electrical tape will solve that problem. And there we go, now the multimeter can't even get a reading anymore. Let's see that, yeah, the probes are still connected. So I'm looking at the Raspberry Pi pinout, on my phone here, and I can see that the third pin from the top is a ground. And if we take the fourth pin on the other side, that is GPIO 4. And also, the good thing about having an optical isolation is even if I short all this together, nothing will happen to the Raspberry Pi. If I didn't have this, I would probably pay a little more attention to the wires and stuff going on here. But we should now be able to hook the power up to the Raspberry Pi. And it looks like maybe some funny business is going on with the GPIO pin, because now we only get 1.4 megohms. And if I disconnect it, you can see it jumps straight up to 50 megohms again. That's probably because we haven't set it in the software yet. So I'll just plug in a Wi-Fi dongle, and hopefully it will reconnect to the network by itself. We'll see if we can connect. Nope. It's because I need to use the IP address. I remember now. So that's that. Of course, this is only local ports on my local network, but if you open up the ports on your router, then you can do exactly the same if you travel halfway around the globe. So what we did is we connected from the computer to the Raspberry Pi using SSH, and that gives us a terminal just like if we opened the terminal on the Raspberry Pi. So from here we can, depending on our user rights of course, access all the files and do stuff, open programs on the Pi. So I downloaded a library from the internet called Wiring Pi. And we have some examples. And it's called Blink. So we will modify this file. And this, as you can read here, it's Gordon Henderson's work. So all credits to this guy, but it's basically free software, so as long as you follow this license you can do pretty much whatever you want with it, it looks like, but read the license. We include the wiring.py and stdio files. Then we define our LED pin. This was a 0, I just changed it to 4 just now. Then we print out to the terminal screen Raspberry Pi Blink. We run this function. It's not a part of this file, so it must be in the library. It's probably some routines that we need to run for the software to work. Then we set the pin mode of our LED pin to an output. So all this is basically the same function names as Arduino so far. I haven't looked at it except this file. Then we enter a for loop. A semicolon in a for loop is just a loop that runs forever, just like a while one loop. Then we set the pin high, we wait 500 milliseconds, we set the pin low again, and we wait another 500 milliseconds and we set it high. So now the multimeter that I'm using here is a little bit slow, so we'll set this to 1500 instead. You can press I to insert. Oops, we were already in insert mode, sorry. But if you wasn't, you could press I. So we'll write, what? Oh yeah, that's right, the numpad doesn't work, by the way. Maybe it does on American keyboards, but not Danish keyboards. So you have to use numbers up here. So that's that. Escape to exit the insert mode. Then you write :WQ for write and quit. Then we can compile it. GCC blink. Oh, Oops. I think that's C. Okay, so that didn't work. Okay, so that didn't work. So we tell it to link to that library that we included. And we'll see. Yeah, that was better. So now we have a file, a.out. Let's run that. Okay. So let's try again. Well, it looks like I got the pin out wrong somehow. It's pin 7. Yeah, so now that worked much better. 1.5 second isn't even enough to see the resistance here, so I'll increase it even further. And by the way, if you have a program that runs in a forever loop like this in Linux, you can just press Ctrl C, and that will exit. It's not supposed to be a Linux tutorial though, but I for insert will take 5 seconds. That should be good enough. Right, quit and compile, run. So you can see now we got 42 was the lowest megohms when it's off, and 700 ohms, 800 ohms when it's on. So I think that will be good enough. So let's stop it. We'll edit the file here so that it's not in a for loop anymore. And we won't keep it on for 5 seconds. Let's just say 1 second. We will recompile and we'll just do a test. So it should only run for 6 seconds. Yep. So now instead of connecting to the multimeter, we will connect to these wires. Like that. And now when I run the program, the computer should turn on. 3, 2, 1, go. And what do you know? It actually worked. First go. So that will be it for this video. And again, you can find the Wiring Pi library at this guy's website. You can just search for it on Google. It will be the first thing that shows up. So I think the most powerful thing about this is that you can do this from anywhere in the world using the Raspberry Pi. If you want to use the Arduino, you don't need any extra libraries. You can just use the code directly in the Arduino software. And I mean, you can also get Wi-Fi modules for these Arduinos, but once you get there, I think it's much easier to work with the Raspberry Pi. And we'll probably get back to this when we have to set up the server also. If you haven't seen it, I built this computer in a previous video. I plan to use it as a file server and maybe to run some applications on it also. But I don't want it on all the time, so it consumes a lot of power. And that's where the Raspberry Pi comes into place, because that only uses 2 watts. So I can ask the Raspberry Pi to turn on this computer when I need it, and then I can shut it off again. And the plan was that I can do that from wherever I am, so if I'm not at home, then I can still turn on the computer and get to my files. But as I said, we will get back to this computer in a later video. Now let's see if it works for shutting it off as well. I don't really need that function because I can always shut it down when it's on. But let's see. Yep, it worked. So, as you saw, this is working now, but we get 700 ohms across the resistor when the LED is on. That is a little bit higher than I wanted it to be. So I might end up putting a transistor in this path here. And then I'll probably put a little bit of resistance and capacitance on the base of that transistor, making it a low-pass filter. So random pulses and stuff doesn't turn it on. So, thanks for watching this video, and if you liked it, please give it the thumbs up, and I will see you for the next one. See ya!